All right, so I'm going to talk about geometric series. I'm going to do it differently than I have because I just made the video and forgot to record, or I thought I was making a video, so I have to repeat myself over again so that you can see this. So I'm just going to point to my notes and try to clarify because I don't want to do the whole thing over again because we have one more video to do or a couple more to do tonight. So I apologize, but geometric series have a very specific form. So I'm going to talk through my notes because I already wrote them up 5 minutes ago and realized I wasn't recording. So the special form of a geometric series is some constant a times r to a power. And if we write out the terms, you can see here that it's a plus a times r plus ar squared plus ar cubed and so on. And this a is usually the first term of our series. And r is something called the common ratio. Because to get from one term to the next, you always multiply by r. Or you could think of, if I divide successive terms like ar cubed over ar squared, that gives us r, which is this common ratio. So a couple of different ways of writing this series. We can shift everything down and start at n equals 0, and then r is raised to the nth power instead. So this is just some ways of writing geometric series. They always look the same. We've already seen one geometric series, which is in the applet, we saw the series whose base was 0.8. You might remember seeing that in the previous video. This series can be written again in two ways. We can start at n equals 0 and then the power is n, or start at n equal 1 and the power is n minus 1. But the idea here is when it is 0, we have a 1, then it's plus 0.8, plus 0.8 squared, plus 0.8 cubed, and so on. We saw earlier that this series actually converged because we looked at the partial sums and we saw that the partial sums were approaching a numerical value. I'll tell you that geometric series converge whenever that ratio is between -1 and 1. And another way of writing it is the absolute value of the ratio is less than 1. So this series will converge since this common ratio is 0.8, which is less than 1. So we're going to find out a couple of things next. When it why does it converge when r is between -1 and 1? That's one question we'll answer. And the second is, what does it converge to? Can we actually find the sum of this series? And so to do that, maybe I will rewrite. Well, let's see. Yeah, I'm going to rewrite the next set of notes because I think that's easier. So to do that, what we're going to do is we're going to try to figure out what is the nth partial sum of a geometric series? What does that look like? And so that would look like the sum, I'm going to change this to a k, from k equals 1 to n of a times r to the n minus 1, right? To the k minus 1. That's what the nth partial sum looks like. If we write it out, we would have the first term, then a times r, then a times r squared, ar cubed, and so on. And because we're only dealing with the nth partial sum, this would be stopped at a times r to the n. It's the nth partial sum. So if you watch the previous video on series, the way that we would determine whether a series converges, we would take the limit of this nth partial sum. But it's really hard for me to take the limit of that because it has n parts, but I don't know what n is. So it's very hard. I would like to, like we did with telescoping series, I'd like to find an expression for the nth partial sum so that we can actually take a limit for it. And so here's a trick that I'm going to do. You're not responsible for this trick. You're just responsible for the result, but maybe this interests you. Right underneath this, I'm going to write a times the nth partial sum. Bear with me. I'm going to multiply every term in the nth partial sum here by a. So the first, no, I'm sorry, not by a, by r. Sorry, by r. So the first one will be a times r, and I'm going to line it up here. When I multiply ar by r, I'm going to get ar squared. When I multiply ar squared by r, I'm going to get ar cubed, and I'm lining them up right underneath. then a r to the n minus 1, and finally a times r to the n. So, and now I'm going to subtract these two equations. So on the left, by the way, I had written that power incorrectly. So I'm going to subtract. On the left, we're going to have s sub n minus r times s sub n. And on the right, you can see that a bunch of things will cancel out if I'm subtracting. And what we're left with will be a minus a times r to the nth power. This is promising because now I don't have an n number of terms to take a limit for, and I don't know what n is. So on the left, I'm going to factor out s sub n to get the expression 1 minus r. On the right, I don't have to, but I am going to factor out a to get 1 minus r to the n. And now I'm going to divide both sides by 1 minus r. So I have the nth partial sum is a times 1 minus r to the n over 1 minus r. This is an expression for the nth partial sum of any geometric series. Nth partial sum of any geometric series, whether it converges or not. And now we want to know, hey, how do I find out if this actually converges and for what values of r, right? That's we already know, but we're going to figure it out. So what we're going to do by what we did earlier is we're going to take the limit of the nth partial sum. Now I have the nth partial sum written as an expression whose limit I might be able to evaluate. Much better than what we had starting earlier. So now we've got a times 1 minus r to the n over 1 minus r. And notice here that the only term that changes as n grows is this term. That's the only one. So I'm going to look at that limit separately. We're going to examine what happens as n goes to infinity to r to the nth power. And you might remember, I don't know, this is one of our common limits. We know this is 0 whenever an absolute value r is less than 1, or r is between -1 and 1, this limit goes to 0. This is a special limit that I developed earlier. Sorry, somebody wrote a note on Discord and I got distracted. This is a limit that we talked about earlier that I told you, you don't have to know how it's derived or why it's true, but get a feeling for it because it will come up. And so now we know that whenever r is less than 1 in absolute value, that's going to go to 0. And so we can find the actual sum of the geometric series because that will be in the limit, right? The actual sum is going to be what's left when this goes to 0. We'll have an a over 1 minus r. This is the sum of a convergent geometric series. And again, only converges as long as r in absolute value less than 1, which means that r is between -1 and +1. Let me pause the video for a second. Okay, let's continue. I just read on Discord that Nat had written that looks like tomorrow there are no classes either. So I was panicking a little bit, had to take a break. Okay, so sum of any geometric series, as long as it's convergent, is a over 1 minus r. Let's look at some examples. That's what I had done here. So here's an example of a geometric series where the common ratio, if you notice, is 1/2. You can write out the series itself. The first term when n is 1 will just be 3, then 3 times 1/2, then 3 times 1/2 squared, 3 times 1/2 cubed. So we can see that the first term of the series is 3. Common ratio is 1/2, so it must converge because that's less than 1. We know the sum of the geometric series is a over 1 minus r. We can apply that here. A is 3. I'm at this line. A is 3. And r is 1/2, so the sum is 6. If we look at our second example, 5/3 minus 5/9 here, I'll do it with you so it's a little bit easier to follow instead of just reading this off. I'm sure that's not easy. But like I said, this is the second time I'm doing this video because I lost the first. I think I must have saved it to the cloud and you can't access that right now. So if you notice here, I'm going to consider here our first term to be 5/3. This is geometric. You should ask yourselves why. We're always multiplying by the same thing to get from one term to the next. That number that we're multiplying to get from one term to the next is always -1/3. I'm making it negative because notice that every time we have a term, we change the sign. So we have first term's 5/3, common ratio is -1/3. This will converge because we know that R is between -1 and 1, and it's going to converge to the sum, which is first term is 5/3, then 1 minus the common ratio of -1/3. So this is going to be 5/3 over 3/3 plus 1/3, which is 4/3. Here, the 3's cancel. You can think of it as 5/3 times 3/4. Multiply by the reciprocal of the denominator. And so this is 5/4, which is the sum of our geometric series. And the final example here, and again, I'm going to erase this so that I can redo it with you. Let's see at this example, e to the n over 3 to the n plus 1. I'm going to factor out, well, I'm going to rewrite that denominator. It's hard for me to see that this is geometric unless I have both numerator and denominator raised to the same power. So in the denominator, I'm going to write this as 3 to the n times 3. And pull out a 1/3, this 1/3. And now I have sum from n equals 1 to infinity of e to the n over 3 to the n, which can be written as 1/3 sum from n equals 1 to the infinity of e over 3 to the n. Hopefully now it's a little easier to see that this is going to be our common ratio R. If we write out the terms of this series, I'm going to leave the 1/3 on the outside and not worry about that for now. But if I wrote down these terms, when n is 1, we have e over 3. When n is 2, we have e squared over 9. When n is 3, we have e cubed over 27, and so on. So you can see that our common ratio that we multiply term by term is e over 3. First term is also e over 3. Now, since e over 3 is less than 1. And I say that because e is 2.7 something. It's smaller than 3. So this ratio must be less than 1. Then we know we have a convergent geometric series whose sum is going to be the first term divided by 1 minus the common ratio. First term, we know, and I'm not dealing with the 1/3 yet on the outside, but first term's e over 3. 1 minus common ratio is also e over 3. So I'm going to write this as e over 3. In the denominator, I'm going to write it as 3/3 minus e over 3, which is e over 3 over 3 minus e over 3. And this 3 with this 3 cancel out if you multiply by the reciprocal. So this is e over 3 minus e. That's the sum of the series, but remember that we multiplied by 1/3. So we also need to multiply the end by 1/3 here. So our sum is going to be 1/3 times e over 3 minus e. So geometric series that converges because that common ratio is smaller than 1, and we find its sum by using S equals A over 1 minus R. Now remember, if R is bigger than 1 or less than -1, we can't use this because the series will diverge. See you in the next video.